Hi, I'm Dave Brown for Teletrain, and in the next few minutes, we'll be looking at aftercoolers, dryers, receivers, and air distribution systems. Filters, like the one you see here, are a compressor's first line of defense against contamination and the costly damage it can cause. You'll remember we stressed the importance of regular filter maintenance. First, as good as they are, filters cannot remove all the particles of dust or dirt that may be drawn into the compressor intake. And in most cases, any dirt or dust that gets pulled in gets pumped through to the discharge port. Now let's talk about water vapor. As you know, when you hang clothes outside on a line, they dry more slowly on a humid day than when the air is dry. That's because there is so much moisture in the air on a humid day that the amount which is evaporated from the clothes is very small. There is always water vapor in the air, and it is drawn right along with the air into the intake of a compressor, and then it is concentrated as the air is compressed. Most compressors are oil lubricated, and oil gets picked up by the air and ends up going right on out the discharge. So you can see between the combination of the water and oil vapor and dirt and dust particles, the air coming from a compressor may not be very clean. And if we allow these contaminants to move through our system, extensive and costly damage could result. That's why several techniques are used to reduce and in some cases eliminate contaminants. Let's begin right at the compressor output. First, instead of discharging the compressed air directly into an air receiver, it is passed through the device you see here. It's called an aftercooler. As the name implies, an aftercooler cools air as it comes from the compressor. This is the air inlet, and this is the outlet or discharge port. The openings in the housing, here and here, are where cool water enters and leaves. Right here is an important part of the system which you will always have when you have an aftercooler. It's called a moisture separator. This unit removes the water that dropped out in the aftercooler. Here is what a water-cooled aftercooler looks like inside. Air flows in here, passes around these tubes, and exits here. In most aftercoolers, the direction of water flow is opposite that of the air flow. As the air passes over the cooling tubes, two things happen. First, since the air becomes cooler, the air pressure drops slightly. But second, and most important, moisture is condensed out of the air. That's because when air cools, it has less ability to hold moisture. So the water condenses or rains out in the form of moisture droplets. These droplets flow into the moisture separator, where water accumulates. Since with even a small aftercooler, we are talking about a fairly large amount of water, the separator should always be connected up to an automatic drain, similar to the one shown here. There are also air-cooled aftercoolers, which function in basically the same way as the water-cooled. In this case, air is used for the cooling medium instead of water. The cooling air is forced across the coil by a fan. A good water-cooled aftercooler will cool the air flowing through it to within 15 degrees of the cooling water temperature and may condense up to 90% of the water vapor originally contained in the air. Just how important is this? Let's use an example to explain. In many operations, 1,000 cubic feet of air can release as much as 1.4 quarts of water. So even with a medium-sized compressor, say of 100 SCFM, the aftercooler could condense a heck of a lot of water. Running continuously, the system would use 6,000 cubic feet per hour. That's 144,000 cubic feet per day. And at 1.4 quarts of moisture per 1,000 cubic feet, the aftercooler could condense over 50 gallons of water in just a 24-hour period. That's more than enough to take a good long shower. That's pretty impressive. But while an aftercooler does a good job of removing moisture, some systems and applications require air even drier than what an aftercooler can produce. When this happens, we have to use an additional device. And you won't be surprised when I tell you that it's called a dryer. To understand why we often need to dry the air after it leaves the aftercooler, we'll need to talk about something called dew point. Dew point is the temperature at which water vapor in the air will condense out. If you've ever looked closely at a glass of iced tea, you may have noticed that water from the surrounding summer air will condense on the glass, up to a certain height on the glass. This line, the level where the condensation ends, marks the dew point of the air. Up to this line, the temperature of the glass is at or below the dew point of the air. It's cold enough to condense moisture out of the air. Now, when air leaves an aftercooler, it is at a particular temperature, say 95 degrees. And at that temperature, the air is saturated with moisture. It's holding every bit it can. We say that it is at 100% relative humidity. Relative humidity is the ratio between how much moisture is in the air and how much it could hold if completely saturated. 95 degrees is the dew point of the air leaving the aftercooler. If it passed into the system and cooled at all, even 1 degree, the temperature would be below the dew point, and moisture would be released. To prevent this, we dry the air, which decreases its moisture content at a particular temperature. In other words, we take moisture out and lower the relative humidity of the air, which means that the dew point is lower. Now the air can cool off somewhat in the system without condensation occurring. Here are the kinds of drying techniques most commonly used in industrial pneumatic systems today. There is overcompression, refrigeration, absorption, and adsorption. Sometimes even a combination of these methods is used. To understand how overcompression works, we have to explain that if we have air that contains moisture, and if we compress the air to a high enough pressure, we can actually squeeze out the water. That is, force it to condense in the form of droplets. It has to do with what is called saturation pressure. And you'll have to take my word for it, the technique really works. Overcompression is a simple method, but it means we have to compress the air to a higher pressure than we want, and then let it expand to the working pressure that the system requires. Since this is a waste of energy, the use of overcompression is usually limited to small systems. Here is a fairly common and highly efficient type of dryer. It operates on the principle of refrigeration. Saturated air from the aftercooler enters here and exits here, cool and dry. The main parts of the unit are this pre-cooler reheater section here, a heat exchanger here, and this refrigeration unit here, which supplies the refrigerant. This system drawing shows how it works. We can follow the airflow through this chamber here, then through the heat exchanger. It exits here. Now look what happens. This section is called a pre-cooler reheater for a good reason. The saturated air coming from the aftercooler is still pretty warm. It passes around this tubing here. which contains air that has already passed through the coils of the heat exchanger. The entering warm air gives off some of its heat to the air that is exiting. So the incoming air is cooled somewhat, and the air leaving is warmed or reheated. Here in the heat exchanger, the warm air flows through this coil. This coil here contains refrigerant at a very cold temperature. The process is the same as what goes on in an aftercooler. But now, since the refrigerant is so much colder than the water in the tubes of an aftercooler, the air loses even more moisture. The refrigerant absorbs heat from the warm air, cooling it to the point where even more of its water vapor condenses out and flows to this drain. To prevent frost from forming, refrigeration systems like the one we've just described are designed to operate at temperatures no lower than 32.4 degrees Fahrenheit. Here is an important point to remember. If you have a system where extremely dry air is required, chances are a refrigerant-type dryer like this will be used. This type of unit has relatively low initial and operating costs, so it's commonly used in industrial systems. Okay, we've talked about squeezing moisture out of air by overcompression, and we've seen that cooling the air and condensing the moisture out of it is very effective. How else can we get the moisture out? Well, we can draw it out of the air by bringing the air into contact with certain chemical drying agents. There are two chemical processes that are commonly used. One of them is called absorption and takes place in a unit like this one. Here is the opening where the wet air enters, and here is the outlet. There is a drain at the base of the housing so water can be drained off. Here is what the absorption unit looks like inside. The wet air enters here at the base. A screen here holds the drying agent in place. Air flows through the agent, moisture is absorbed, and the dry air exits here at the outlet. Absorption-type dryers use what is called a deliquescent drying agent, which means that the agent will liquefy as it absorbs moisture. In this model, the drying agent is poured into this chamber. During the absorption process, the agent and the water fall to the base of the housing and must be drained off. Since the drying agent liquefies, it must be replenished periodically, which is very easy to do. There are, however, a couple of considerations involved in using the deliquescent drying process. It turns out that some of these drying agents are highly corrosive, which means there is some potential for corroding system components. Also, absorption dryers are not normally recommended for use with air that is warmer than 90 degrees Fahrenheit. At higher temperatures, the desiccant is consumed very rapidly, and there is a possibility that the pellets can soften and bake, restricting airflow through the agent. Despite these disadvantages, this type of air dryer has the lowest initial cost and is the least expensive to maintain of the common air dryers. The other chemical process is called adsorption, and that's adsorption, spelled A-D, not A-B. Adsorption dryers use chemicals which actually hold water vapor in small pores in the drying agent. Two of the chemicals that are being used are silica gel and activated alumina. In fact, you may have purchased a new gun or a pair of binoculars and found a bag like this inside the carton. Well, it contains silica gel, just like that used in adsorption dryers. In this process, the chemical agent is not consumed. That's why an adsorption type dryer, like this one here, is usually a regenerative dryer. It is designed to use the drying agent over and over again. It works like this. While the agent in one of these towers is being used to draw moisture out of the system, some of the dry air exiting from the tower is depressurized back to atmospheric pressure and piped over to the other tower. It is then passed through the agent here and dries it by absorbing the moisture out of it. Then, when the agent in this tower has become saturated, the agent in this tower is dry and ready to be used again. So the unit switches over and reverses the process. Despite their high initial and operating costs, maintenance is generally low. And this is the unit to use if your air must be very, very dry. Before we leave dryers, I want to make a very important point. Normally, dryers are designed to take air after it has been through an aftercooler. High temperatures may be detrimental to the dryer. Now let's talk about air receiver tanks. The receiver tank is used to store compressed air, and it helps smooth out air pulsations caused by the compressor. More important, however, it eliminates the need for frequent loading and unloading of the compressor. And this means less equipment wear and reduced maintenance. Here is a typical receiver. The inlet on this unit is here, and here is the output port. You'll note that the receiver has a drain here so that any moisture or other contaminants that might accumulate during use can be drained off. It's important that the drain be located at the lowest point in the receiver. Every air receiver in use should be equipped with one of these. Do you recognize it? That's right, it's a safety relief valve. The ASME, which is the American Society of Mechanical Engineers, as well as state and local codes, require that a safety relief valve be installed on most units. So if you don't see one, notify your supervisor. Here's an important point. The valve must be capable of discharging the full rated flow of the compressor. Safety relief valves are normally set to 10 psi above the normal receiver pressure, but always below the rated working pressure of the receiver. You'll find that some receiver tanks are very large, while others are much smaller, like this one here. What determines their size in a system? Well, receiver tanks are sized according to basically three factors: the compressor output, the size of the system that it's supplying, and the frequency of air demand. A good rule of thumb is that it is better to oversize a receiver than to specify one that is too small. A large tank adds little to installation cost, and because it can average varying load demands, it provides increased capacity to meet demand surges. It also lowers air velocity in the tank, which improves fallout of condensed moisture and solvents or oils which may be carried in the air stream. Well, so far we've discussed compressed air in the air receiver, where it is stored as potential energy, in the aftercooler, and in the dryer. The next step is getting it to the point of work, and that's the function of the piping system. There are three main types of piping systems commonly used in industry today: the dead end, or grid, the unit, or decentralized, and the loop. Let's see how they differ. This is a typical dead end system. You can see that all air moves away from the source, which is located here. This is called the central main, and these are smaller feeder lines. Outlets are located here, along the feeders. Note that in order to minimize pressure drop, the main is largest here, where the flow is greatest, and becomes smaller further from the source, where airflow has decreased, although mains that are uniform in size are quite common. While the dead-end system is the simplest system to install, and often the least expensive, only one flow path is available. This means that workstations furthest from the supply may get insufficient air if the demand is high. And this may be a limitation for some pneumatic applications. Here is an example of a unit or decentralized piping system. A unit system consists of 2 or more grids, and each grid has its own compressors located here, here, and here. The ability of this kind of system to handle changing load requirements can be improved by interconnecting the individual grids. One big advantage of decentralized systems is that the compressors are located much closer to the point of work. This means you can use shorter supply lines and you'll have lower pressure drops. Most important though, it will provide more uniform air supply and system pressure. The most recommended distribution system is the one shown here. It's called a loop system, and you can see why. It allows for the same size of piping to be used throughout the system, and that gives more equal pressure distribution. If necessary, it's even possible to position air receivers along the loop at points where air demand may be momentarily heavy. So if you did get a sudden peak demand, you'd be able to maintain system pressure and prevent what is called air starvation. Some of you may be responsible for actually making new pipe installations. So here are a couple of points with which you should be familiar. First off, when you're laying out a distribution system, try to keep the number of fittings you use to a minimum. Remember back in Lesson 3 we talked about friction and changing fluid direction? Fittings and bends, no matter how well made, add greatly to system friction, and this leads to pressure drops in the line. So if you want to keep the efficiency of the systems you install high, keep the number of unnecessary fittings down. Here's a drawing that shows several common system components. The main, a header here, and a drop leg which feeds this automatic drain. When you're hooking them up, remember to connect supply headers to the top of the mains. That's so any moisture in the main will be swept on by and won't get to any power equipment. Water legs with automatic drains should be located at low points along the line. This will help to reduce further the accumulation of moisture in the system. Finally, distribution mains, feeders, and headers should be installed with a small slope. This will help condensation move to the drain points. Hear that? Know what it is? You're right. It's a piping air leak. And although leaks in pneumatic lines do not present a housekeeping problem like a leak in a hydraulic line would, they do waste air, reduce system pressure, and often reduce air tool performance. For instance, in certain cases, a pressure loss of just 10 psi can result in a drop in tool efficiency of 15%. That's why it's important to be on the lookout for air leaks. As you heard just a minute ago, serious leaks are often audible, and a good time to listen for them is when most of the plant is shut down, like at a shift change or on a weekend. To find smaller leaks, all you have to do is carefully caulk the windows and doors, then flood the plant with water and look for bubbles. I'm only kidding. Actually, for smaller or suspected leaks, soapy water, like this guy is using, or commercial leak detecting fluid can be very effective. The air escaping from the system will cause the fluid to bubble, as you see here. The method works just like checking for a leak in a bicycle tire. This concludes Lesson 6 of Parker Hannafin's Industrial Pneumatic Technology. The exercises for this lesson are on page 58 of your text. I'm Dave Brown for Teletrain.